Math466, lecture 26, advanced applied analysis. So what we're going to do today is we're going to prove that if there is no cross, it contributes fully. And then hopefully prove if there exists at least one cross, it doesn't contribute in the limit. And then that will allow us to do the first half of the proof of the density of states for the eigenvalues. It will give us what the average moments are. Then we have to identify a distribution that has these as the average moments, but we'll at least now know what to look for. So you're asked to think about, so here's a theorem. If no crossings, then contribute fully. And we've shown that the number of crossings is the Catalan numbers. So we got to the point where I think we had 1 minus the square root, or I think 1 minus 4x all over 2x. And we now needed to just use Newton's generalized binomial theorem to expand that out. And so if there's interest, I'm happy to go through that calculation later, but it's a pretty standard calculation, just expanding this out, and after some algebra, getting 2n choose n, 1 over n plus 1. All right. So here's the question. So I have some number of dots, and I'll just put dot, dot, dot in here, so I don't have to worry about do I draw an even or odd number of dots. I have to make those dots look smaller than these dots. So here's one, I guess, L1, L2, and L2M, L1. And I have things matched in pairs, no crossings. Any thoughts as to how we can show that it contributes fully? Or any thoughts about what must be true in a configuration like this? There must be a certain type of structure that must always exist. Something must happen. And the goal is we want to reduce things to smaller problems. So let's assume by brute.
Do you need that an adjacent pair is always connected?
So that some excellent. Some adjacent pair must be connected. I don't know which ones. So without loss of generality, relabel and assume it's this one. What would happen if no adjacent pairs were connected?
There must be a cross.
Well, one, two, three, four, five. So let's say I have something like this. Now I have something like this. And I have no crossings. So by induction, there must be an adjacent pair that's connected.
Yeah.
Well, what if it was like this? And what if the adjacent pair that's connected was actually this one? Then by induction, again, I have a smaller set, and there must be an adjacent pair that's connected. And again, if it's this one, then by induction, there's a smaller one, and eventually you get this. So no matter what, if there's no crossings, there must be at least one pair that's connected. Must there be more than one pair? Let's assume we have at least 4 vertices. I think you need at least 2. We don't need this result, but we now know this by induction has to have a pair that's connected.
We're gonna choose one adjacent pair to start, and then reduce it down pairwise to some terminal set of two vertices.
Yep.
And those are connected, and there's your starting point.
Right. So we actually know there have to be at least 2 pairs that are connected. We don't need 2 pairs. We just need 1 pair. But it's nice to see how far can you push the argument. There has to be a second one. What's nice about this? Well, let's look at all the different indices. So L1, L2, L2, L3, yada, 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 L2M minus 1, L2M. Now, because these are connected, L1 is in the same for both of them. So what must be true about L2M and L2?
Yeah.
They must be the same.
So we get at least 2 fixed.
So what I want to do is I want to lift this edge out. And so we now have a Catalan number here. We still have no crossings in what's left over. I want to somehow remove this edge. If I remove this edge, I lose L1, but L1 was free. So we remove the L2M, L1, L1, L2. So free was L1.
Well, now we can redraw our graph.
Yep. So fixed was L2M.
We replace L2M with L2.
So we replace L2M with L2. And now,
choose some adjacent pair.
but now this is exactly what we wanted. This is now lower.
Yep.
Now have decreased number of vertices by 2. Still no cross. And now by induction, this contributes fully. And then all that's left to do is the Princess Bride fix. Right? What's the small problem? It's mostly free, right? I've removed one matching. And so when I have all these other pairings down here, I have to make sure that none of them equal that. Or I would have a 4th moment or a 6th moment or an 8th moment. But since I only have k pairings, then the number of things I lose is a function of k, not a function of n. So when I divide by my high power of n, it's not going to matter. And so in the limit as n goes to infinity, it will contribute fully, or mostly fully if you want. The correction is negligible. So what I like about this is it's a really nice, elegant argument that you just have to worry about. I'm sorry, that if you have a Catalan configuration, if you have a configuration with no crossing, it contributes fully. And it comes down to you lift one out, and then you have something smaller, and by induction you're done. So if we just have just 2 vertices, that was the very straightforward case of just the second moment. If it was even 4 vertices, it wasn't too bad. Okay. Any questions about the adjacent case? All right, so the adjacent case isn't bad. So now what's left is, of course, the non-adjacent case. In different random matrix ensembles, the crossing cases can contribute. But they will only contribute when your matrix has more structure. So for instance, Toeplitz matrices are constant along diagonals. What that means is if you want to match, you have lots of different candidates to match with. Right now, if I want to match, I only have 2 candidates. Myself, and then flip the indices. So if I'm A34, I've either got to match with myself, or I've got to match with A43. That's it. If you're constant along diagonals, well, now you have on the order of n things to match with. And now you have more chances. And that's why these other cases, these crossing cases, they can contribute in other ensembles. In the full real symmetric matrix ensembles, we don't need to worry about that. If there is a crossing, no contribution as n goes to infinity. L1, L2, L2, L3, L2M, L1, L2M minus 1, L2M. So this is a bit harder in terms of what's the best way to do this. One of the things you can start to do is you can start splitting this up into special cases. And maybe some cases are easier to handle than others, but you have to make sure that the cases are inclusive and cover all possibilities. There's some cases for the crossings where it's very easy to prove that there's no contribution. Any thoughts as to what might be the easy case? The one where you're matched opposite? Where everything is matched opposite? Yeah. That would be a calculation. That would be a calculation. But if you have a crossing, then you can So that may be a really good one to look at. But there's a special case where if a certain match happens, by induction we know that there can't be a contribution. Well, but that could be your full long ones like this with lots of things in between.
How about if like L1, L2, and then you leave one in the second one?
So if I match this to here?
Yeah.
But then we're going to solve we have to do that calculation. I'm saying you're close, not matching it down to here, but where should I match L1, L2 to? What did we just do a moment ago? If we match it here, we now have an adjacent matching. We can lift that up as we did before. And now by induction, we have a cross over here. Could there be a cross into this one? No, because it's adjacent. So if you have any adjacent matching, you can remove that, reduce to a lower case. So if there exists an adjacent matching, remove, done by induction. Is there always an adjacent matching? No. We have lots of configurations where they know. So the first one was the star. We also have crossings like this. You could have crossings like this. So there's a huge number of cases where you don't have adjacent matchings. So it's a nice thing to try. I don't know how helpful it is. Now what it could come down to is later, we might be in a situation where we can say, well, if there was an adjacent matching, we would then be done, and we know there's not an adjacent matching. So if we ever need that, we can definitely use that as a result. But for now, I unfortunately don't see a way to have this help us. Okay? So sadly, this all gets erased. So there has to be a cross. So what it would mean is we've got to have something like this, and then something in here going through that to something down here. And there's a lot of ways to go about this. I'm not sure if all of this is needed, but to me it's the thought process behind this that matters. You are never going to be calculating average moments of random matrix ensembles after you leave Williams, unless you have a massive life change. Okay? So I don't really care in some sense about the answer. I care more about the thought process as to how you would attack this. So we could have multiple crosses. Which cross should we work with? Is there any way we could try to order the crosses or associate something to them? So let's look at this. So good. So I like the idea of the smallest cross. But I will put it in quotes. So what do you mean by smallest cross?
It's with points that are closest together, adjacent.
So treat me like a moron. What do we mean by points closest together? I've got 4 points.
Those 3 would be adjacent.
Okay, so let's label the points A, B, C, and D.
Maybe choose 2 points that aren't connected, and how many spaces are there in between them?
So let's look at, so the number of points between A and C is the smallest in everything involved in a cross. There's no crosses that have fewer. There might be another cross that has the same number, but there's nothing that has fewer. So that's, I think, a really good way of doing smallest. And this might have been exactly what you were saying, but you have to phrase it really carefully as to what do we mean by smallest. Because if you look at the distance from here to here, plus the distance from here to here, plus here to here, plus here to here, that's going to be constant. You could also look at the smallest distance between 2 points involved in a crossing. Choose any crossing where the distance from A to B is as small as possible. So let's try the number of points between A and C is the smallest of all crossings. So if I have another crossing anywhere else, the number of points it has must be more. So what do we know now about the stuff between A and B and the stuff between B and C? Okay, so now we've got, so here's A, here's C, here's B. I have some number of dots here, some number of dots here.
If they're connected to each other, if they form more crossings?
So if anything in here is connected to anything else,
it cannot be connected on this side, right? Because then it would cross it.
okay, so nothing from here. Wait, could this be connected to something down here?
No.
Why not?
Because then you would have. Oh, but then that could be the smallest crossing.
That could be the smallest crossing, because if this is connected down here, I still have the same number of points between A and C. So these points can be connected down through here.
Not that.
And they could be connected down here as well. Can there be any crossings in these points?
No.
Can there be any crossings in these points? Can there be any crossings with these points and these points? Can any point here be connected to any point in here? Why not?
Because AC is supposed to be the smallest one.
W-
Definition, we would have another smaller one.
Right, so if we connected anything from here to here, it's a smaller crossing with BD. So if we call this group 1 and we call this group 2, there's no matchings between group 1 and group 2. And that would violate minimality. So this is one of the big techniques we have, is you take some quantity and you look at the minimum value. And as long as you're looking at a finite set, there will be a minimum value. There could be many choices, so choose one of them. And then you show that if something else happened, it would violate the minimality. So now we know all of these things here are either matched amongst themselves or they are matched outside. Similarly, these are all matched either with themselves or outside. And there can't be any crossings in here, because if there was a crossing, it would violate minimality.
Couldn't there be a smaller cross?
I'm sorry?
I just see the smallest one there.
So we've said that this configuration is the smallest cross. If there was a cross in group 1, then we didn't have the smallest one. Because clearly there's fewer dots here than going all the way from A to C. At the very least, we've lost B. So we know that there can't be any crossings here. They can't be matched down here. They can be matched in a catalog configuration, or they can be matched coming down on outside. So the goal is we want to show that we somehow lose a degree of freedom. In every pairing, we have at most 1 degree of freedom, except for the first pairing where we have 2. So for this one, this crossing here gives us 2 degrees of freedom. I'll just write DF for degrees of freedom, because that's our initial crossing. Now we start moving over here. So if this was L1, L2, L2, L3, L3, L4. Let's say these are coming down and through here. L2 is free, right? I'm sorry, L2 was determined from here. So L2 we already know, so L3 is free. And then it comes down here, and it's going to fix some stuff down here. We come to the next one. We've already chosen L3 from here. L4 is free. And comes down and chooses something in here. And we keep going like that until we come all the way to here. And so, do we agree that the first component here is going to be determined? As we march down the line, the first component will be determined. If we ever had any adjacent matchings, we can just lift those. So the first component of B is free. I'm sorry, it's fixed. First component fixed. And that's what L2 was fixed, was free here and then became fixed here. L3 was free here and then became fixed in the next one. So over here, when we match whatever was right before that down here, the first component of B is now known. Now let's start over here. Let's say this was LK plus 1. Well, if we come up over here, this is LK minus 1, LK. This has to be matched with somebody. LK was known. LK minus 1 is now free and gives us something down here. Or if it wasn't free, then we've already lost a degree of freedom and the problem is done. So LK minus 1 is free here, and now up here, LK minus 1 is known. So now we have LK minus 2, LK minus 1. LK minus 1 is now fixed. LK minus 2 is free. And so when we keep propagating up over here, now we get second component is fixed. So we attack it from two different sides. So now the two components of B are fixed. And when it comes down over here, it fixes everything here up to maybe flipping the order. But we don't care about powers of 2. We only care about n dependence. We only care about the number of free variables. So because of the crossing, we actually see that the two indices of B are fixed. We don't have anything free in this crossing. And now we've lost a degree of freedom. And each matching gives us at most 1 degree of freedom. We're done. Then you could say, well, what if instead of being matched down here, it would be matched over there? It would be a similar type argument. It would still be passing information. It might even be worse that you might have lost something earlier. So your best case is keeping as many things free as long as possible. You will see that as you get to here, and of course there's no way any of these things could be matched with this because this is matched down here. We're assuming we have a crossing. So you can now see why I chose not to write this proof up in the book. This is a much better proof to give verbally at the blackboard with chalk, drawing pictures, and arguing informally than to write this up carefully. There's lots of proofs of this. I like an argument along these lines. I think it really highlights what's going on. It has this nice concept of minimality. But now let's step back and see, do we actually need that concept of minimality? So we were saying these were all matched down below. Well, what if they were matched internally? Would that really make a difference? It would just mean we have maybe fewer things that are free. And so I think the same argument would go forward even if you didn't assume that this was the minimal. It's just minimal is a really good way of making a lot of these arguments. Okay, so this finishes up the Catalan component of the lectures. We've now calculated the moments. We've seen that the moments are the Catalan numbers. Do people want to go through the Taylor expansion, or are people happy leaving it? So if anybody wants to see it, this is the time to speak. If not, I will just say use Newton's generalized binomial theorem. If you haven't proven it, it's worth proving. Okay. So now the question becomes, we have a sequence of moments, And the moments are basically the Catalan numbers with powers of 2. And the powers of 2 are coming from the fact that we are adjusting our distribution to live between -1 and 1. So Wigner's semicircle law says basically that it's going to converge to a semicircle, and we've normalized things so that the semicircle is going from -1 to 1. So the density is going to be some constant times the square root of 1 minus x squared. What is that constant? Right? It has to integrate to 1. Right? So we know, and because it's even, we can just integrate from 0 to 1 and double it. We'll go 2c square root of 1 minus x squared dx equals 1. So this is a senior capstone class. Let's go all the way back to calc. How do we evaluate this? I heard at least one person asking for divine inspiration. There's a great quote, as long as there are exams in school, there will always be prayers in school. So you can put it to Mathematica. The North Koreans detonated a nuclear warhead, destroyed all of our electromagnetic systems. Internet is down, your computer is fried. You have to do this by hand.
Don't you do x equals 10?
I'm sorry?
Can you use trig identities?
So you can use trig identities. So which trig identity do you think of when you see a 1 minus x squared?
X equals sine or cosine.
So it's x equals sine or cosine. Do you want sine or do you want cosine?
Either is good.
Yeah, I was going to say, we can use either one.
Right. I might do sine because at 0 I have 0, and if I do sine I would be 0.
Okay, cool. So sine.
So do we want to try x equals sine of u? And then what would dx be? Cosine of u du, and we don't have to worry about minus signs. If x goes from 0 to 1, then u goes from what to what?
0
To pi over 2. Whenever we are doing anything involving differentiation or integration, we use radians. You can talk informally of, it's a right angle, it's 90 degrees. But we have to write down pi over 2 as soon as we do differential trigonometry. Otherwise, the derivative of sine is not cosine. I always like to do a little bit of pedantic writing like this so that you don't screw up the bounds of integration. So this is the same as 2c integral u goes from 0 to pi halves. So we have the square root of 1 minus x squared. Bless you. So we have the square root of 1 minus sine squared u, and now dx is just cosine of u du. But the square root of 1 minus sine squared is cosine squared. So we get, this is just 2c integral from 0 to pi halves of cosine squared u du. Anybody remember how to integrate cosine squared u du?
What did do cosine 2u?
The double angle, not the double angle, but like.
Oh boy, we get to do double angle stuff. Wonderful. Right? No, because, well, okay, so let's see if we can do this.
Is double angle correct?
Yes. So cosine of 2u is cosine u minus sine u sine u. Right?
Probably.
Yes?
Looks familiar.
This is the angle formula for u plus u. With the when it's plus, it's minus. So you get cosine of 2u is cosine squared of u minus sine squared of u. But what's sine squared of u? 1 minus cosine squared. So you get cosine of 2u is 2 cosine squared u minus 1. And so now cosine squared of u is 1/2 cosine of 2u plus a half. So now we feed that in, and we get 2c integral from 0 to pi halves.
Cancel really nicely, so that's really nice.
Well, sure, yeah, we'll kill the 2, that's fine. So we'll have cosine of 2u plus 1 du. All right, well, the integral of 1 is just pi halves. And now we have to integrate cosine. What do we get when we integrate cosine?
0 to pi, right?
0 to pi halves, I thought.
Well, it's 2u, right?
Oh, it's 2u.
So we can integrate cosine from 0 to pi.
Well, we would put a 2u here and then a 1/2. Then we would get a sine of 2u.
Yeah. 0.
But the integral of cosine is sine,
Yeah.
because derivative of sine is cosine. So we would have the sine of 2u over 2 at 0 and pi halves. Right, because the sine of pi is 0. So we get c times pi halves equals 1. So we get c is 2 divided by pi. Okay? This is like Calc 1, Calc 2. Okay?
We could have done this a way easier way, I think.
There is a way easier way, and I want to actually discuss the way easier.
That's a semicircle, and that has area like pi, right? Maybe.
Pi halves.
Pi halves, right?
It has area pi halves.
Pi halves, right? So it's like, yeah.
How do you know the area of a circle is of a
Semicircle is pi squared over 2.
How do you know that? In some sense, we've just proven this.
Oh.
No. It's no.
Right.
No. This is I lost a friend to engineering when he on his freshman homework he proved that it was an integer and he proved it equaled 1/2, and then the professor or the graduate student TA wrote, "You now must prove that 1/2 is not an integer." And he basically said, "Check, please. I'm done. I'm going to go to engineering."
Check.
Yeah. He had enough. How do you know that the area under this is pi over 2? How do you know that the area of a circle is pi? Do we need that actually when we're doing the differential trig? So in some sense, if we've already assumed...
No, because you're building the circle from like its constituent components of sine and cosine, but like, why can't we just do the way?
Well, but I'm saying we might have already essentially had this when we were calculating the derivative of sine as cosine. We needed to take this limit of sine of x over x. We need some knowledge of the circle for that. And so we might already have had that the area of the circle is pi. So it may not actually be a bad assumption to say, come on, we already know that. So it becomes a real challenge at times to figure out what are you assuming and when did you assume it in all these calculations. There is a better way to do the integration though. So once we get to this, we're integrating cosine squared from 0 to pi halves. Do you agree that this would also be the value of cosine squared if we went from negative pi halves to 0? Let's look at what cosine looks like. Cosine starts off at 1, comes down, goes up. But now if we square things, so this would be cosine, and if we square things, cosine squared, be a little bit higher, come down.
I don't think it'd be a little bit higher, Professor.
Oh, sorry. You're right. It would be the same. You're right. It would be the same height. You're right. It would be the same height. Thank you. It would look like this, right? So notice that from 0 to pi is essentially reflected. 0 to pi halves is reflected from pi halves to pi, and then you get the same thing, going on and on and on. This is just 2c times 1/4 the integral from 0 to 2 pi of cosine squared u du. Because from 0 to pi halves, it's the same value as pi squared, as pi halves to pi, pi to 3 pi over 2, 3 pi over 2 to 2 pi. So all I have to do is calculate the integral of cosine squared and then divide by 4. What would you like to integrate instead of integrating cosine squared? 1. How can I replace this with 1? What is preventing this from being 1? What does this want to make it 1? Sine squared. What's the integral of 0 to 2 pi of cosine squared relative to the integral from 0 to 2 pi of sine squared? Is there a difference between integrating cosine squared from 0 to 2 pi and sine squared from 0 to 2 pi? No, sine and cosine are just shifted functions. I'm sorry?
Yeah, okay.
So this is the same as 2c 1/4 1/2 integral from 0 to 2 pi of cosine squared u plus sine squared u du.
Right.
And that's 1. We can integrate 1 without too much trouble. So we get 2 pi. The 2's cancel. And so we get c 2 pi over 4, which is pi over 2. Which proof is better? This proof or that proof?
The one where you look at the circle.
Okay, or the one where you look at the circle.
Yeah.
So we have three proofs, right? Which proof do you like? Circle has area pi halves. This idea of saying, well, cosine squared, I can relate this to the full period, and then I can just put in the sine squared. Or I have this nice formula for cosine squared as 1/2 cosine of 2u plus 1/2. The answer depends on what you need this for. If all you're doing is calculating this one integral, I would probably say it's pi halves. This gives you a nice technique to handle a bunch of integrals. Now what's interesting here is we aren't getting an antiderivative. We're only able to evaluate certain full integrals. But it means we don't have to go through the challenge of finding the antiderivative. This computes the antiderivative. It's a lot more work. We get a nice identity as a consequence. But we're going to want to calculate not just the area under the curve, we're going to want to calculate the moments. So you had a divine inspiration that it was pi halves. Well, what if I now put in an x to the k over here and ask you to calculate the kth moment? I think for 50% of the k, you can do it quickly.
Right.
Which moments can you calculate very easily? Try again. Odd. Right. This is an even function. Right. It's an even function. So if I give you an odd moment, it has to be 0. So all the odd moments vanish. That's not a problem. So we now have to calculate the even moments. So, and we'll come down over here for the start. So the 2mth moment would be the integral from 0 to 1, and then I have to double it. X to the 2m square root of 1 minus x squared dx. All right, if you are divinely inspired, please speak up. So the circle of pi halves has now been eliminated. It just doesn't generalize well. It doesn't help us well with the next stages. It got us the normalization constant. It's the best for getting the normalization constant. But in terms of now getting something that we can use. All right, so now let's do the trig substitution as before. So if we do the trig substitution, we'll have 2 integral u goes from 0 to pi halves. What's x to the 2m going to be? Sine to the 2m of u. Now what's the square root of 1 minus x squared dx? Well, we just showed before that that's just cosine squared. So that's the integral we need to do now.
Lovely.
Yes. I now have the song from My Fair Lady, Wouldn't It Be Lovely, running through my head.
We do our magic completing cosine squared.
Well, it would be wonderful, wouldn't it?
Yes.
So we'll call I2m is 2 integral from 0 to pi halves sine to the 2mu cosine squared of u du. There is a way to do this without too much pain. What technique? And it's not going to be trigonometric substitution because we've already done it.
Parts.
Integrate by parts. What should we let u be? What should we let dv be? So let u be cosine of u, and dv will be sine to the 2m of u cosine of u du. Right? So basically, we're going to split up the cosines. Yeah, they had a good one. The sine to the 2m really wants a cosine. So it's good. We're going to borrow one. This is very similar to how we did the Gaussians. So now, du, derivative of cosine, minus sine. And the mnemonic I always have is you have to remember where to put the minus sign. It's minus sine. All right, dv. No, this is the most common mistake, is dropping where the sign is. All right. How many of you know SOHCAHTOA? Yeah. Okay. I always have to derive what SOHCAHTOA is for my knowledge of trigonometry. So it's never really helped me. What would be v if dv is sine 2m?
So just sine 2.
Sine 2m plus 1.
Sine 2.
Doesn't that become 1 minus cosine squared to the
Oh,
n?
sorry. Some sick changing thing.
Just sine 2m. U.
Well, the derivative of sine 2m would then be 2m sine 2m minus 1 times cosine.
Okay, so 1 over 2m plus 1.
And how many powers of sine do I have?
2m plus 1. Yes.
So this could be a little bit troublesome. It looks like we're getting higher powers of sine, but we're getting rid of all the cosines. So we now have the uv boundary term. Well, what's nice is when u equals 0, this is 0, and then when u equals pi halves, this is 0. So we don't care about the boundary terms. The minus signs cancel. So we get I2m is equal to 2 integral from 0 to pi halves. We'll have sines to the 2m plus 2 of u over 2m plus 1 du.
Yeah.
Does this help or not help? So we start off with 2m plus 2 trig functions. We ended up with 2m plus 2 trig functions, but now they're at least all sines. So the question is, did we make any mistakes anywhere? Is this okay? Okay. Now there is another way we can attack this. How could we write cosine squared of u? We can write it as 1 minus sine squared, right?
Yeah.
So if we use cosine squared of u is 1 minus sine squared of u, we get I2m is equal to twice the integral from 0 to pi halves. Should have just dropped the 2's. And then we'll have a sine to the 2m of u minus a sine of 2m plus 2 of u du. So if we let j of 2m be twice the integral from 0 to pi halves of sine of 2m of u du, what do we have? we have I of 2m is what? It's j of 2m plus 2 over 2m plus 1 from this part, right? And this equals this part over here, j of 2m minus j of 2m plus 2. So this is, I called it the bring it over method. One of my students many years ago in differential equations named this. You have the same quantity on both sides. Bring it over. As long as the coefficients aren't 1, this is going to be beneficial. So I now bring this over, and I get j 2m plus 2 over 2m plus 1 plus this. So I have 2m plus 1 over 2m plus 1. So we get 2m plus 2 over 2m plus 1, j 2m plus 2 equals j of 2m. And I still have like 2 minutes left, plenty of time. So we get j of 2m plus 2 is 2m plus 1 over 2m plus 2, j of 2m. Oh boy, more recurrences, right? We've seen recurrences many times this semester. This is nice in that it's a recurrence of depth 1. It's not nice in that the coefficient depends on m. All right, but it's not horrible. Now, if you look at this, whenever you see an equation, always ask, is it reasonable? Does this seem reasonable that j2m plus 2 should be smaller than j of 2m?
Sorry, I'm not, how did we get the j2m plus 2 divided by 2m plus 1?
That's from here. Remember we did the integration by parts? When we did the integration by parts, we got this. And now that's just j2m plus 2 over 2m plus 1. And so we use the integration by parts, and then we also use the cosine substitution. So we attack the integral 2 different ways. And by attacking it 2 different ways, we were able to get a relationship with an expression we want. So we didn't have the original integral, but we had something closely related to it. And so now we have a recurrence relation.
Can we actually calculate the closed form?
Yes.
Okay, cool.
Yes. And based on the time, it will almost surely be on Wednesday. So the only question is this reasonable that why is it reasonable that the moments are getting smaller?
The sign is between 0 to 1 and you take a higher power.
Yeah, so we have the integral of x to the 2m times this. As m gets larger and larger and larger, x to the 2m is going to be getting smaller and smaller and smaller, except at 2 points, 0 and 1.
Yep.
And so basically it's getting smaller everywhere. So it makes sense that the moment should be getting smaller. So what we'll do on Wednesdays, we'll actually figure out how to get a closed form for this. What do you think this should be related to? It should be related to the Catalan numbers. So it should be related to binomial coefficients which are factorials. Can you see factorials emerging from this? Yeah, we're going to be doing these things, and since we skip every 2, maybe that's where, I don't know. Although we don't have exactly double factorial with the Catalans. We have a 2n factorial over n factorial, but then one of the n factorials can cancel. You'll have powers of 2. Then you'll be left with the double factorials coming in. So it does seem reasonable. So at the end of the day, it looks like it could work out.